Hello there, students. We're going to be going into our third lesson on energy right now. The title of this lesson is The Law of Conservation of Energy. I want you to stop right now. If you haven't completed lessons 1, 2, or the e-science lesson for this week, please go back and do that before starting on this one. Otherwise, it's not going to make a heck of a lot of sense. So if you've already done that and you feel like you understand that, congratulations. You're ready to understand how awesome this is. Not only can energy have different types and different forms, but you can actually find that they can be transformed between each other. We've mentioned that already a little bit, but today this is what we're talking about. So the objectives for the day, for this lesson at least, to describe how energy can be changed from one form to another, which is called a transformation, in order to describe how it moves through a system and is always conserved. We're going to talk about what that word conserved means in a minute. But yeah, you have the same amount of energy. What does it mean for energy to be conserved is our big question. And what is an energy transformation? They're pretty related. Before we get started too far into this, I want you to do an investigation. For this, we're going to be making a pendulum. Pendulums, you may have heard of that word before or seen something like this, but they're all over the place. They're not just a ball that's attached to a rod. But in general, that's the idea. You have a connection on the top, a long, rigid object, which means it's not moving or bending, and then an object on the end of it, a weight. That doesn't need to look that way. If you were to, say, use even a shoestring and tie it to an apple, you can use anything, and your hand can be the top part. So what I want you to do is make a simple pendulum, test it, basically. Try to figure out how it works. Try and answer these questions. Why does a pendulum move the way it does? Maybe you can describe the forces behind it. Does a pendulum have energy? If so, what kind of energy does it have? Forms and types of energy does it have? And then the last question would be, does its total energy amount change, or does it remain the same, constant? So I'll ask you to pause this video, go get your supplies and try it out, and then come back as soon as you're done. Okay, imagining at this point that you have tried it out. You may have figured out some cool stuff. I'm using my wife's necklace right now. She's asleep, so she doesn't know. This is a pendulum, I guess you could say. I'm going to make sure that actually you can see it. Okay, yeah, you have a pendulum here. I'll try and make it a little bit shorter. It's just a necklace. I'm going to hold it at the top, and also you can see that there's the actual necklace itself in the bottom. Notice if I let it go, and it will go back and forth pretty quickly. If you notice it's a regular repeating pattern. We call each one of those back and forths a cycle. And the time it takes for it to go back and forth, this isn't on a test or anything, but it's important to know about pendulums, is called the time period. They're all related, and if you may have found out, or I'm sorry, I'll try this out right now. Try and figure out how to make the time period slower or faster. If you could add more mass to it, do you think that would affect it? If you increase the length of the chain, would that affect it? If you even change where you start from, would that affect it? Pause your video, try it out. Okay, coming back in here now. I'm not sure how good you scienced it, but if you say that the mass affects it, you're making that up. The mass doesn't affect how long it takes for a pendulum to go back and forth. I could add more mass or less mass. For example, I'll just show you a quick example of that. If I'm using this chain like this, it goes back and forth about 1, 2, 3, about every second. If I take that same length of chain, but instead use something that doesn't have the actual pendant on it, I'll just use the chain this time. It has very little mass at all. 1, 2, 3, 4, 5, 6. It's actually the same exact amount of time. So the mass on a pendulum doesn't make much of a difference. Kind of surprising. Second, if you were to change even maybe where it was held from, say it starts here, if I hold it all the way up on the side, does that make it go faster than it would have otherwise? Let me take a look. 2, 3, 4, 5, 6. Doesn't seem to. Even if I put it down here, 1, 2, 3, 4. It happens to be the same. The only thing that affects pendulums really is the length of the pendulum. The longer I make it, the slower it becomes in terms of the period it takes to go back and forth. If I were to shorten this thing up, something like this, I go back and forth very quickly. That has nothing to do with energy. It's just interesting things about pendulums. I love them. If you take a look now at the presentation, pendulums are actually interesting for our purposes today because they're a great example of the conservation of energy. When I say conservation, I mean that energy can be conserved. It doesn't just disappear. We learned about potential and kinetic energy last time, and even the forms of energy. If we're looking at this, there is kinetic energy where the pendulum's moving back and forth, but you know that it stops at this point and at this point, and at that point, basically potential energy goes up to 100% of it, and there's no more kinetic energy. At the very bottom of it, when it's moving the fastest, it doesn't have any more potential to go any further. So all the energy has become kinetic energy, moving energy. If you're having a hard time with understanding potential and kinetic energy, this is very similar to the energy skate park on the PHET, which you're going to be doing later. So hopefully that'll help out. And also just, you might take a look back at the previous lessons about potential and kinetic energy and how they're measured and understood. So right now we're going to start with our notes. That was just an introduction. If you can go ahead and open up your guided notes, which are, you should look for them here. It'll be posted to your classroom post. We're going to be starting up here. There's not very many notes to take, and then the rest of these lessons for today will be on reviewing. So once again, get your guided notes out. And as soon as you're ready, let's keep working on our notes now. This is one of the most important things in science. This simple statement here, it might not seem that simple, but you'll get used to it. It's called the law of conservation of energy. You remember there's the conservation of momentum, which means that the momentum that goes into a system is the same that goes out of it. We use that with the bouncy balls and billiard balls. When one hits another, it's not like the momentum goes away. That's because energy is conserved. Going back to this, in a closed system, say a closed system just meaning, hey, if this is a place that energy can't come out or come out of or into, say it's planet Earth, and all of a sudden we just put a big bubble around Earth and we said no more energy can escape or come in. In that closed system, the total amount of energy is fixed. If the Earth blew up and it turned into 1,000,000 pieces, it would still have the same amount of energy that it had before it blew up. Not that that would happen. It just would look different. So let me read this full statement out. In a closed system, the total amount of energy is fixed. You can't create any more energy inside the system or destroy any of the energy that's already in there, but you can convert the energy you have from one form into another. So we've already kind of seen that potential energy and kinetic energy can be transferred into each other. We haven't talked about how that works out for specific forms of energy yet, but if you have a cart like this little simulation over here, you notice that the TME stands for total mechanical energy, all the energy of the cart. At first, it has only potential energy because it's not moving, but it's up on a hill, and then as it moves, it goes down, and all that potential energy gets turned into kinetic energy. But notice, at each time, the total energy doesn't change. The total energy being all the moving energy and the stored up energy. This is basically what the conservation of energy law means. There's some really cool applications of that we're going to get into, but especially to know that if you transform one form of energy into another, you don't lose energy in the process. It can be transformed into multiple different types that maybe you're not expecting, but you don't lose it. So some applications here. If energy can't be created or destroyed, where did it come from? Not trying to answer that question today. It's very confusing to me too. Energy is conserved when a change in form occurs. And anytime you see this underlined word at this point, you can go back to your notes and take that. It's conserved, meaning it doesn't change when a change in form occurs. When this ball, the pendulum, we call it a bob, when the potential energy gets transformed into kinetic energy. This is gravitational potential energy getting transformed into mechanical or motion energy. The amount of energy here and here are actually exactly the same. A lot of people would say, oh, it's up here, doesn't have any energy at this point because it's not moving. That's not true. It has the same amount of energy here, here, and here, just looks different. Like mass, you can't just destroy or create mass. You can't destroy or create momentum. That is a central fact of it. So say in our science class, if we were sitting in our science class, if we lock the doors and close the windows, it's not like anything's spontaneously going to come out of nothing. We're not going to have something appear in there in the form of energy or matter. And that seems like obvious, but when people try to make machines that produce energy out of nothing, it's impossible. It's a fundamental law of physics that they call the first law of thermodynamics. Other applications, energy can only be transferred or transformed into other forms of energy. I guess it's technically possible for energy to be turned into matter, but that's just very, very rare. It's actually much more common that matter is turned into energy. Even energy and matter are two forms of the same thing. It's like two different sides of the same coin. For example, in a star, the star takes matter in the form of hydrogen and helium, and it turns it into pure energy, which comes in the form of heat, thermal energy, and radiant energy. The last point here, energy is often transformed into thermal energy from friction, but it's still energy. So when you have two things, say my mechanical energy, my hands pushing together right now, they are the amount of energy in from this side and the amount of energy in from this side. It seems like, well, where's it going? And a lot of that is just turning into heat and sound. If you can hear it, if you can feel the heat of it, you know that that's where that energy went. And now the energy's in the air around it, the sound's in the energy around it. A lot of it just seems like it disappears, but it's really just out there now. There's not as much of it. It's kind of like if you were to think of like spreading butter over a huge piece of toast. The energy might look different. You know it's there. It might even look different. Now it's melted. You don't even see it. But just know that it didn't just disappear into thin air. Just before we get into talking about how energy can be transformed, I want to review the forms of energy real quick. Check my time here. Okay, yeah, we should have enough time to talk about this. Forms of energy, we talked about a couple. These are 6 here: thermal, mechanical, nuclear, chemical, and electrical. Just for example, nuclear energy. Say nuclear energy inside of a sun or a star, they have fusion happening where inside the nucleus of the hydrogen and helium atoms in our star, they are getting fused together, and in the process some of that matter gets turned into energy. So the transformation here would be the energy that starts out as potential nuclear energy is getting ripped apart and turned into all sorts of kinetic energy, stuff that's moving. You think about that, it gets turned into electrical energy, probably some of it. It gets turned into lots of thermal energy, and visible light, for the most part, is what it actually transforms into as far as we can see it. You see it's a big burning hot ball of plasma because there's so much transformation of its nuclear energy into light that travels across the solar system. If it didn't work that way, if the energy wasn't able to be transformed, that would be like a white dwarf, which it doesn't have a potential for transforming its nuclear fuel anymore into heat and light. So we're going to do some practice here, but I'm going to start this up in the next video. So for now, just pause, actually exit out of this video, and take a look at the second video on Google Classroom.